All right, what we're going to cover today is we're going to kind of shift gears. We're really actually pretty much done with the core Java concurrency part of the course, which is great. That's a lot of stuff, as you can see, and it's also very fundamental, whether you're using Android or you're building server-side applications or you're building stuff for laptops or desktops, whatever. If you're using concurrency, chances are a lot of the stuff we talked about will be relevant. But now let's bring it back to the Android side of the house. And what we're going to do here is we're going to talk about some of the more domain-specific Android concurrency frameworks and programming idioms, and I'll explain what those things mean. Before we do this, though, let's take a quick tour through what we've covered so far, just so you are aware of where this next part fits into the grand scheme of things. So here's kind of a picture of the stack that we've been covering in the course so far. This stack is somewhat idealized. In other words, there could be implementations of Java that don't have exactly the layers here, but most of them have something quite along these lines. And as you all know, Java is designed to try to balance performance, runtime performance, and human developer productivity. And that's why there are layers, right? If we were just worried about runtime performance, we would program at the low levels. If we were just worried about the productivity, we would use some very, very high-level framework or domain-specific language or something. But Java's trying to strike a balance between the two, and we'll talk about that. So, of course, at the operating system kernel and system library level, you've got threads, operating system threads. You've got things that abstract away from the hardware, the multiple cores. You've got system libraries like libc or pthreads. This is sort of the high-performance side of the house, where the goal is to get you as close to the underlying computing elements as possible. But most people don't like to program at that level because it's very tedious and error-prone. So Java then provides a couple of other layers, right? So there's a virtual machine layer. That's part of the Java runtime. We talked about that. That's where you get sort of the built-in Java concurrency features, things like threads, things like monitor objects, things like synchronized blocks, things like volatile, and to some extent you also get some of the atomic operations we discussed briefly, like compare and swap. Those kinds of things occur at the virtual machine layer. And of course, underneath the hood, they're leveraging system libraries and operating system stuff and hardware. But that's a distinct layer that's provided to you through the JVM. On top of that is then the Java util concurrent classes. That's really this part up here. And that includes a lot of things we've been covering. So that includes reentrant lock, reentrant read-write lock, phasers, stamped locks, semaphores, condition objects, abstract queued synchronizers, all that kind of good stuff we've been covering. Those come out of the Java util concurrent part. All right, so that's pretty much all we've covered to this point. And if you think about it, there's a lot of things we covered. There's a lot of abstractions and classes here. The final layer we're going to cover is termed additional frameworks and languages. We're not going to cover the languages part. Languages would be other languages like Scala or Clojure or other types of higher level, often functional programming languages that abstract away and layer on top of the Java virtual machine. They're called JVM-based languages. We're not going to cover those. What we are going to cover is the additional frameworks part. And these are basically domain-specific frameworks. And of course, the ones we're going to cover are the ones that have to do with Android. So Android provides you a bunch of things above and beyond all the stuff that comes underneath in the stack. And that's what we're going to start covering today. All right, well, let's start talking about why do we need this stuff, right? What's the reason why we've got this additional layer on top of all this other stuff? Why is it not sufficient just to provide you with the Java stuff that we get out of the box? So one of the main reasons for domain-specific stuff is because the things that are not domain-specific, the domain-independent layers, in this particular case, Java util concurrent or Java threads or other stuff like that, the JVM, those are not sufficient to meet some of the more idiosyncratic constraints of the Android environment. So Android has a bunch of constraints that it applies, and you have to learn to live with them. And frameworks, domain-specific frameworks, have evolved to make those constraints more tractable. So here's a nice picture of a constraint, right? The poor little Android robot is being crushed by a vice. And you can learn all about some of this stuff here. So what are some of the constraints? Well, you've seen some of these constraints already. So the classic one of the classic ones is you can't let the user interface thread block for any length of time, beyond a second or two, a couple seconds. Otherwise, you get the application not responding dialog generated. So that's an example of a constraint, right? So what do you do about that? We'll talk about it. And you can learn more about that if you haven't already seen it. So what this means is the user interface thread can't block for long duration operations. Likewise, and this is sort of recap, the non-user interface threads can't access the components in the user interface toolkit since those components are intentionally not thread safe. And there's a bunch of reasons why they're not thread safe, because A, it would make them slower, and B, it would make them error prone because you would have to try to figure out how to do all the programming of your user interface widgets in a concurrent environment, which is really complicated. So they just said, we're not even going to try. We're not going to let you do that at all. Now, the stuff you get out of the box, all the things we talked about before, the Java concurrency mechanisms, they don't give you enough capability in and of themselves to cleanly solve these problems. Now, of course, you can build abstractions yourself over top of the Java synchronization and concurrency mechanisms. But that's exactly what Android does for you, right? It pre-builds you these abstractions. So therefore, obviously, Android provides domain-specific concurrency frameworks, and they are going to encapsulate some of the idiosyncratic behavior of the underlying Java infrastructure and Android infrastructure to make it work better. Now, why do we do this? Well, it's really the same reasons why we use concurrency in general, right? Why do we use concurrency? We use concurrency for several reasons. One is because why not? There's lots of cores running around. Let's go for it. But more specifically, we want to use concurrency in order to be able to improve software quality factors and attributes. So simplify program structure, we talked about that, so you don't have tangled mass of event-driven code. Speed things up by being able to overlap computation and communication, so these application threads run on processor cores, and also give this perceived responsiveness where even if you don't actually have things running faster, people feel like it's running faster because they're not sitting there waiting for this hourglass to wrap up. Okay, now the other thing we're going to talk about in this intro, because this starts to get really important to understand how these things work, are all the patterns that are used. And you'll see that you can, in fact we will, explain some of these Android concurrency framework capabilities purely in terms of the APIs that they expose. You can do that. You can learn that stuff, make sense, more or less. But two things. First of all, you'll often be sitting there scratching your chin wondering, why do they do it quite this way as opposed to some other way? What's the motivation for why it looks like this? So learning to be a full stack developer, learning to be a software professional is more than just sort of taking an API at face value. You also want to know why it looks like that. And you want to know why it looks like that because someday you may be called upon to do something similar, and it would be helpful if you understood how it works. And you may also want to know why it works the way it does because you may need to optimize it or debug it. So that also helps as well. So it turns out that patterns help to explain how the APIs are developed because the people who built the APIs in the first place were some of the world's leading experts on concurrency patterns, like my buddy Doug Lee. So it makes perfect sense for us to understand the patterns that they used when they built the abstractions so we can do a better job of understanding how they work and how to use them effectively. And we'll see that there's a whole bunch of different patterns. Okay, so that's a quick overview. Let's now go ahead and start talking about what goes into the concurrency frameworks themselves. So we talked about why we have the concurrency frameworks. They shield developers from some of the weird quirks of Android, and they enhance software quality attributes. So here's a more specific drilling down on some of those capabilities. So here what you can see is we've got some long duration, potentially blocking operations that are going to be able to run in background threads. And there's going to be a couple different ways to do that. One way is for you, the application developer, to spawn those threads and then to use them in conjunction with other framework components and patterns to glue it all together. That's one approach we'll look at. And then there's another approach where it kind of gets baked into a more cohesive object-oriented abstraction, and you can work with that. And that's really cool because it applies a lot of the patterns we've talked about in 251 and elsewhere. But the basic idea is long-duration threads run, or long-duration operations run in background threads. And then short-duration operations, the ones that interact with the user, run in the one and only user interface thread. So that's all single-threaded. And we'll talk very shortly, certainly by the end of the day, about the patterns that help to motivate why they separate things like this and what that's called and how you could see this pattern in other languages, other technologies, and so on. The particular example we'll use, which we've talked about a couple times before and you'll get a chance perhaps to play around with it before the class is done, is the concurrent download application where we're basically using an activity which gives the user a menu of things to click on to provide a URL, and then a bunch of ways to download the URL with different techniques. And a bunch of stuff gets done. There's threads, there's other background stuff called services we'll talk about later, and so on. The point is that this allows us to be able to decouple the user-facing processing from the background processing. All right, so these background threads will run the long-running jobs for this thing, and then there'll be a queue, the synchronized message queue, which we'll talk about how that works in a second. It doesn't quite use any of the Java mechanisms out of the box, but it's not unlike some of the Java mechanisms. There'll be a synchronized queue that's used to pass messages between the user interface thread and the background threads, and vice versa, depending on which way you're trying to go. In fact, most of the communication in this type of model is actually from the background threads to the user interface thread, not the other way around. The user interface thread, as we'll see, is also perfectly capable of passing messages to itself. So if it needs to do something in the future, or it wants to remind itself of doing something, it can create a message and stick it on its own message queue and then process it when that message's turn down the road. There are two primary concurrency frameworks in Android. Now, there's other stuff that it provides above and beyond what we're going to cover. There's some very, very, very domain-specific things like stuff for doing computational imaging and stuff called the render script framework. There's also something called RX Java. We're not going to talk about either of those frameworks. We're going to focus on the main things that Android provides with out-of-the-box Java programming. The first one we're going to look at is handlers, messages, and runnables, which I like to call the HaMeR framework. And this allows operations to run in one or more background threads. And as these background threads finish up their job, they stick the results in a message that's processed subsequently by the user interface thread. Now, as we'll see as we start talking about this stuff, this framework is cool and it's fairly straightforward to use, but it requires you, the application developer, to understand certain things. You have to understand how to spawn threads, which shouldn't be any big deal at this point. You have to understand how to create runnables. You have to understand how to create messages if you use the messages variant. And you have to understand how to pass these things in the right way between various parts of the system. So things like handlers, messages, and runnables, and threads, all that kind of stuff are things you have to understand how to deal with. Not the end of the world, it just requires some additional stuff. So this is sort of more like, it's like an erector set where you're given a bunch of pieces and you have to assemble it into something or other. Right? It doesn't come pre-assembled for you. The second abstraction, which is much more pre-assembled and more cohesive, is called AsyncTask. This also allows operations to run in the background, in one or more background threads, and it allows the results to be published to the user interface thread either periodically or when everything's finished. However, unlike the HaMeR framework, it doesn't require the application developers to have to know anything whatsoever about threads or handlers or messages or runnables. All you have to know to use the AsyncTask framework is simply inherit from AsyncTask and override a bunch of hook methods using the template method pattern. So it's a variant of the template method pattern. Once you know template method, understanding AsyncTask is really simple. I tend to like AsyncTask because I'm an object-oriented person and it feels really familiar and comfortable. It's also really concise. It's a very beautiful framework. It's interesting to read it under the hood. It uses all kinds of cool patterns. If we have time before the class is out, we'll look at that. If we don't have time, I did a video from a class a couple years ago where we did have time, so we covered that, and you're welcome to go look at it if you're curious. All right, so that's the place to go look for more information about AsyncTask. Each framework has pros and cons. We will cover them in great depth. I will not ask you on the quiz Wednesday what are the pros and cons, because we won't really have covered them in any detail yet. But be aware that there are definitely pros and cons, and they're used throughout Android and throughout Android applications very, 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 very heavily. Another thing to keep in mind, just so your knowledge of abstractions in this space are comprehensive and well-founded, both of these frameworks embody what we know as idioms. So these are Android-specific concurrency idioms. An idiom is basically a pattern that's very specific to a particular context or a certain context. So for example, there are patterns for particular development environments. The development environment or development platform, the patterns you might use for Unix might not quite be the same as the patterns you would use for Windows or for Mac OS or something like that. The different development platforms. There are also platforms that differ based on programming language. C++ patterns are often somewhat different from C patterns or Java patterns or C# patterns or JavaScript patterns or ML patterns, right? If you're taking the programming language class, you're familiar perhaps at this point, perhaps more than familiar than you want to be, with Prolog or ML and these other paradigms. And they have totally different patterns than C++ and Java use. And those are called idioms. And there's even design methods. There are different ways of designing software, right? There's object-oriented design, structured design, functional design, and so on. And so all these different things have different ways of doing stuff. And you can go here and take a look at idioms to find out more about that. So the frameworks that exist in Android are good examples of idioms that are specific for the Android environment. If you're programming in some other environment that doesn't have these constraints, like you're programming a massively parallel supercomputer, you probably won't have the user interface thread type of thing, right? You'll have a different abstraction, and you would use a different kind of concurrency environment. All right, so that's a quick overview. Now let's start to dive a little deeper. Now, we're going to take a look at the rest of these discussions from two vantage points. The first vantage point we're going to talk about is really the class-centric point of view. We're going to talk about the classes, and I'll refer obliquely to the patterns that these classes embody, but I won't spend much time on them. And then the next set of slides, which we should get to today, flips things around. Then we're going to talk about the patterns, and then we're going to make oblique references to the classes that embody them. Now, in real life, when we give a talk, we have to sort of pick one thing and talk about it first. It's very distracting to try to say three things at the same time. You get lost. So we have to go in a certain order. So I'm going to talk about the classes first and then the patterns. But once you understand the patterns, we could certainly talk about the patterns first and then just show how the classes embody those patterns. Either way is perfectly acceptable. And you'll see some of the patterns we'll cover are ones you should be familiar with. So that should be much easier. All right, so here's basically the whole enchilada, all the different pieces we're going to talk about. And we're going to talk about the classes that are visible to programs. Those are the tip of the iceberg. And we're also going to spend a little time talking about the classes that are sort of hidden from programs. These are the stuff that's underneath the surface. And I find it interesting to understand both layers. There's obviously even more things we could talk about, but knowing these classes, knowing how they work, will give you a firm basis in a lot of concurrency abstractions. Even if you're not programming Java, you'll find this stuff useful over and over and over again. Not surprisingly, these are based on patterns, and we'll talk about some of this stuff as we go along. We're going to cover the most important classes in Android's concurrency frameworks. There may be some other auxiliary classes that are lurking deep in the bowels of stuff we're not going to cover, but if you look at the source code, you'll find out interesting stuff about them. Some of the classes are used both by the HaMeR framework and by the AsyncTask framework. So some things you get double duty. We'll talk about runnables, and you'll see how they're used in both environments. We'll talk about handlers. You'll see how they're used in both. And other things are very specific to a particular environment, especially the AsyncTask framework. So let's first start by talking about one of the simplest mechanisms that is provided here. This is one of the invisible classes for the most part. You can program it to it directly, but it's typically invisible. And it's called the looper. Wasn't there a movie called The Looper, or something like that? I'm trying to think who it starred. Was it Bruce Willis? Bruce Willis, yeah. It looked like one of those movies where you have the time-space paradox. If you go back and kill yourself in the past, that's a very common theme, obviously, in science fiction. So a looper is used to run a message loop for a thread. Now, what you're going to see here, one of the first things that Java does, one of the first things that Android does, is it takes your garden variety notion of a thread, which you've already been exposed to, and it goes one step further, and it adds some stuff to the thread. And it's going to go ahead and add this notion of a message queue. And each thread is going to have a one and only one looper. So in an Android environment, when you have a thread that you want to make a looper, then there's an API call that you call, and that creates a looper object that resides in something called thread-specific storage. And we're going to talk about thread-specific storage shortly. It's a pattern that's implemented in Java using the thread local class. This is a class that you very, very rarely run across unless you're implementing frameworks like this, where it's used all the time. And the whole purpose here is that each thread has its one and only looper, and that's used as a message pump. We'll talk more about that. So the looper, basically, there's one looper per thread, and thread-specific storage is a pattern that's used to enforce that constraint. And then we also have something called a message queue. And the message queue is then layered on top of this, and it's used to hold the list of messages that a looper will dispatch. So you can imagine the purpose of the looper is to sit here in a thread waiting for something to do. It's going to call loop. And when there's something to do, then a message will show up in the message queue. And we'll talk later about how the message gets in the message queue. But the message shows up in the message queue by some means, not yet revealed. And the looper will pick each message out of the queue one at a time and then dispatch the message. And it'll call back its appropriate hook method to do the stuff with it. And there's some other things we need to get that to work. But that's basically the idea here. The message queue holds the list of messages that will be dispatched by a looper in the context of some other things we're about to talk about. And the message queue uses the monitor object pattern. So we've seen monitor objects already. And you know that monitor objects are basically ways of being able to ensure only one thread at a time can call into an object on a class. And you'll see how monitor objects are used to be able to add messages to the queue. And then there's one thread that can pull messages off the queue and go ahead and dispatch them. So that's the monitor object pattern. Keep in mind that that might or might not use Java's built-in monitor objects. It may use a totally different mechanism, as we'll see under the hood, but the pattern is what matters there. Okay, so we talked about message queues. Those consist of messages. Well, what is a message? So a message is a very important abstraction in Android, and it contains a description of the type of message, what kind of message it is, and you can control what that type is. And it also contains some arbitrary data object. In other words, it's a type object, right? So you can put whatever you want in there. And this data, plus a few other things that you can kind of slip in there as well, can be sent to something called a handler, which we'll talk about in a second, via the message queue. So a message is basically something that is a description of some processing to be done or some result. It's really up to the receiver to know what to do with it, the handler to know what to do with it. But a message just provides an abstract description of the type of the message and perhaps some data that the message has to work on. There's some other really cool things messages provide that we won't really have a chance to talk about till later when we talk about some of the inter-process communication mechanisms in Android. But for right now, we're just focusing on concurrency. So you can learn more about messages here. Messages are not created directly. You never say new message. Instead, you go to the message class and you use a factory method called obtain message or obtain, and that will go ahead and make you a message. And the reason it does that is under the hood, Android's concurrency frameworks keep a pool of allocated messages. So for those of you who are taking the operating systems class, I think you talked about malloc somewhere in that class. And if you recall, malloc has like a bunch of free messages of various sizes that if you want a 4-byte or 8-byte message, it just grabs one off a free list and says, here you go. So messages are very similar. They have a pool of messages, and you can allocate them very quickly and deallocate them very quickly because they come out of a pool. That also has some really quirky characteristics. If you do not remember that messages come out of a pool, strange things can happen. But we'll talk about that when we get later into the discussion. So factory method pattern is used to make the messages. Now, so far we've talked about how do you have a looper that's associated with a thread via thread-specific storage. And we talked about how that looper also has a message queue that holds queues of messages for something to process. But we haven't really said what does the processing. So the next thing we're going to talk about is the what does the processing. And that's something called a handler, which makes sense. Someone's got to handle the processing, right? So the handler allows threads, often background threads, to send messages and or runnables to another thread, although it can send it to itself if it wants to, but it usually sends it to another thread where it's put into that thread's message queue, and then the looper in that other thread will pull these things out and then use the handlers to go ahead and dispatch the processing of the messages. And we'll see there's a couple of different ways to do this. One of them is to basically use dispatching of runnables, where you call the run hook method, or the framework calls the run hook method for you. And the other thing is to call something that's called handle message. And we'll see both of those things being used. We can use handlers in conjunction with loopers, message queues, messages, threads, blah, 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 thread-specific storage, all this good stuff we just talked about. We can use all these mechanisms to implement a couple of patterns we'll talk in more detail in a second. In particular, the command processor pattern, which is what's used when you have runnables with a run hook method, and or the active object pattern, which we'll also talk about, which is where you're sending messages from one thread to another. Very cool patterns, and learning about those patterns will help you understand lots of other things in the concurrency world. A runnable is a very, very simple abstraction. You hopefully all know what a runnable is at this point. A runnable is basically a command or a task that can be executed by having its run hook method called. And runnables, as you recall, have no return value. They just do their thing. If you want to get a return value back, there's some other tricks you can play, but by default you just say run. Okay, so all the things we just talked about, looper, message queue, message handler, runnable, these are all the abstractions that you need to understand in order to program the Android HaMeR framework. And what you typically play with as first-class citizens in that framework are messages, handlers, and runnables, and then loopers and message queues are kind of hidden from you, but they exist underneath the hood. And we'll talk about them next class or whatever. There are also some other classes that are just used by the AsyncTask framework, which does a heck of a lot more stuff on your behalf. And here are some of the classes that are in AsyncTask. So one of the things is called future task. If you recall our discussion of the executor framework, if you go back and watch the videos, you'll see a discussion of future task. And future task was used by the completion executor service in order to be able to take the results of two-way asynchronous invocations on callables and then be able to take the result when the result is done and stick the completed future into a completion queue, which can then be processed in another thread of control. So future tasks are often used for executing something, and then when that execution is done, getting the result put back someplace else for subsequent processing. And that's exactly what they're going to be used for in the AsyncTask framework. Future task is used to start and cancel an asynchronous computation. In other words, it can run on a separate thread of control. Query to see if the computation is complete. In other words, see if it's got a result yet. And retrieve the result of the computation when it's available. So future task gets used. And when we look at the implementation of AsyncTask, which by the way is really super cool, we'll see how that gets used. The other thing that's available is the executor framework itself, which, as you remember, is a way of decoupling thread creation and thread management from thread behavior and application behavior. And what this will be used to do, it'll be used to execute runnable tasks based on the policies you have configured when you use AsyncTask. You can either run these things sequentially, or you can use a pool of threads, and so on. And we'll talk in a minute about some of the cool patterns that you'll know and love, like strategy and so on, and template method, that can be used in conjunction with all the plumbing that Java gives you in the executor framework to build an object-oriented abstraction that's easier to program and reason about. All right. This particular pattern implements the half-sync, this particular abstraction implements something called the half-sync, half-async pattern. Okay, what I'd like to do now is talk about how the Android frameworks for concurrency map onto the more general concepts of frameworks. Now, those of you who took 251, I think we covered frameworks very briefly. I said about 5 words about them in a couple places, because it wasn't really a frameworks class. This is a frameworks class, so we can talk about them more freely here. So the classes that we've just talked about in Android work together, as you'll see that's the very definition of a framework almost, to embody key characteristics of frameworks. Here's what a framework is. A framework is an integrated set of components that collaborate to provide a reusable architecture for a family of related applications. That's a good definition to just know. If for no other reason, it usually shows up on a quiz. So that's what a framework is. And there are three main things that frameworks do, which are also important to remember. Number one, so-called inversion of control. So what happens here, as you see with the looper, is, and there's a couple other places where it's used as well, the looper owns the thread of control. It's sitting there blocked, waiting for something to do, right? It yanks the thread of control out of your application's hands and grabs onto it and says, mine, 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 right? And when something interesting happens, it dispatches callbacks on registered tasks or handlers or whatever, right? That's what inversion of control means. Inversion of control is sometimes humorously referred to as the Hollywood principle, because it says, don't call us, we'll call you back, right? So you can always remember inversion of control equals Hollywood principle. The second thing that frameworks have is so-called domain-specific structure and functionality. What that means is, as we've been talking about, right, a framework is not just a generic collection of classes intended to be used everywhere. It's intended to be used in a more specific domain. And it has both structure, like handlers, messages, loopers, all this kind of stuff, which are above and beyond the generic threading and synchronization mechanisms Java gives you out of the box. It gives you those domain-specific structures, and it also gives you a whole pot of functionality, like the order in which things are called, the default algorithms, the canonical control flow, all of that kind of good stuff too. So that's another thing. Frameworks have domain-specific functionality. They're not just a box of Lego bricks that can be plugged together any old way. And then the third thing that frameworks have are so-called semi-complete applications, or in the case of Android concurrency frameworks, portions of applications. So what that means is that there are certain hook methods that are left uncompleted by the framework that you are responsible, you the application developer or the infrastructure developer, are responsible for filling in and overriding and customizing as you see fit. Can anybody think of a couple of examples of hook methods that are used by the concurrency frameworks we've talked about so far? Run, yeah, exactly. So run, process or handle message, and then when we talk about the async task stuff, you'll see that it would be things like do in background or on post execute or on pre execute. These are all hook methods that you fill in the blanks, and then the framework does all this other kind of gobbledygook in the background to make it all work. And when you look at the async task framework, or when we look at the async task framework later, you will see there's a lot of gobbledygook going on in the background. But you have to know just about a couple of different places to fill in the blanks. So it's very cool. We'll analyze all this stuff as we go through here. And of course, all of this ultimately is then layered upon by the application framework portions of Android. So other things like the window manager and the activity manager and the notification manager, blah, blah, blah. And then the applications also use this stuff as well, either directly or through the application framework. So as you see, when you look at the code, this stuff is absolutely used everywhere in Android. So knowing these abstractions, you've got to know these abstractions to program anything other than completely non-trivial, very simple user-facing applications that say hello world. Some of the classes we're going to look at are visible to application developers, runnable, handler, message, and so on, and executor. Others of things are less visible. They're sort of hidden. And executor, if you don't want to see exec, you don't have to see the executor, but you can see the executor if you want to. Other stuff is more hidden. Then, of course, it's all based on patterns.